My name is Nazar. I am a student of electronics from Ukraine. In our experiment we need to measure the form of very large voltage signal. The signal at peak reaches 3000 voltage. In addition, the signal has a high frequency, about 300 kHz, but our oscilloscope can measure up to 350 voltage. For measurement this signal, we decided to make a voltage divider. This device divides the voltage by 10. Here is the circuit and the results of its modeling. As you can see, the voltage divides by 10. V in is 3000 voltage and V out is 300 voltage. The output voltage equations is that. We have produced such device. The board has 10 resistors of 100 kΩ each, connected in series. The output signal is taken across the resistor R1. For our test, we have programmed the controller. It forms a square voltage signal across the load resistor. The signal has the following parameters. Peak-to-peak voltage is 20 voltage, duty cycle is 50%, and frequency can be set from 1 to 2000 kHz. This is that signal, its signal. This is a load resistor R1. This is an inverter, our MOSFET transistor. And this is our divider, this board. We tested our device and found that our divisor is not able to pass the higher frequencies. As you can see, the signal at a frequency of 15 kHz is very distorted. That's it. Very distorted. And at 115 kHz, frequency selective and completely disappeared. This is due to the influence of parasitic capacitance, which are contained in the resistor, wires and other. Carry out an analysis of our problem. Input impedance of oscilloscope is 1 megaohm. The input capacitance of the oscilloscope is 25 picofarad. Thus, the overall circuit of our device is that. In the circuit, CR1 is parasitic capacitance of the resistor R1. CR2 is the parasitic capacitance of the resistor R2. COSC is the input capacitance of the oscilloscope, and ROSC is the input impedance of the oscilloscope. This is voltage divider. The output voltage for the overall circuit is this, where Z1 is this, Z2 is found from these equations. Z1 is impedance of that, Z2 is impedance of that. XCR2, XCOSC and XCR1 is the impedance of capacity. This, and this. The magnitude for the overall circuit is this. V out divides by V in. For the future work, we need to determine the unknown parasitic capacitance CR1 and CR2. For example, for a frequency of 10 kHz, input voltage is 5.55 voltage, this, and Vout is 0.50 voltage. And for 50 kHz, Vin is 5.57 voltage, Vout is 0.13 voltage. In final, we get the following figure. It is magnitude of Vout divides Vin versus frequency omega. Substituting the values of magnitude obtained in the experiment in equations 1, we obtain the system of equations. This system of equations has two unknown parameters, it's CR1 and CR2. Solving this system, we found that CR1 is 1.5 picofarad and CR2 is 105 picofarad. Simplifying our circuit and assume that R1 sum is R1, CR1 sum is CR1, C2 sum is Z, C2 sum is Z. We get before and after our circuit. R1 sum, CR1 sum, this resistor and this capacitance. These formulas. The problem of compensated voltage divider has been discussed in Anand Agarwal books Foundation of Analog and Digital Electronic Circuits, Chapter 13. If we choose one particular values of C1 sum such that the real output time function is independent of frequency. This. From equations 1, CR1 sum is that 13.5 picofarad. This is a circuit. This means that if we increase the capacity C1 sum to 13.5 picofarad, then expression 3 this will be executed independent of frequency. To do this, we put a capacitor of 16 picofarad in parallel to capacitor C1 sum. We get the following circuit. This is a capacitor, and it has capacity 16 picofarads. To do this, we can determine the magnitude of Vout divided Vin versus frequencies omega. We measure the input and output voltage for different frequencies and write these values in our table. Frequency is 100 kHz. This is from square signal. And now frequencies is 300 kHz. This is form of signal. And now frequency is 1000 kHz. we get 1000 kHz, and this is form of signal. Square signal, good square signal. And now we get frequency 2000 kHz, 2 MHz. The signal is a little distorted, but is so good. Again, put our values in the table. In the frequency 10 kHz, V out is 5.35 and V out is 0.5, and the frequency 50 kHz, V in is 5.37 voltage and V out is 0.51 voltage. And we get this figure, this red figure, and as you can see, this blue figure is before modification, this red figure is after modification. We have a good magnitude. Now we get a good compensated voltage divider and we can finish our experiment. This is waveform of IGBT transistors in half bridge inverter. This signal have peak-to-peak voltage 3000 voltage, and its frequency, this is in this region, is about 300 kHz. This frequency is 3000 Hz. As you can see, he is not distorted. That's all. Good luck.